So you might ask, what's all this source transformation stuff good for? So I want to show you how you can use it to solve circuit problems. So here we're asked to find a voltage across an 8 ohm resistor at the far right hand side of the circuit. And we can do this by simplifying starting from the left hand side. So we've got this kind of messy network over here which has got 3 different sources in it. And you might think, wouldn't it be nice if instead of 3 different sources, if I just had one, right? So how can we convert this? How can we simplify this circuit? So in particular, I recognize here a kind of a real voltage source. So that's an ideal source in series with a resistor. And I know that I can simplify that. So in particular, I can take my my first branch, so that's this bit here, and I can turn that into a current source, which will be in parallel with a resistor. And the resistance stays the same, so it's going to be 20 ohms. And the amount of current that I have, so the current here, IS, is going to be my voltage, which was 120, divided by the resistance, which is 20 ohms, which is 6 amps. So I have here a 6 amp current source. And so this part that I've just drawn is the equivalent circuit of the yellow highlighted section. So replacing that voltage source with a current source. I can now go and do the same type of transformation for this component, although I'll need to be careful about the polarity because you notice that the plus and minus signs are the other way around, which means that this as a current source is pushing current down the page, whereas the first one was pushing current up the page. And so the current for this one, IS, is going to be my voltage, which was 60, divided by my resistance, which is 5. This is just Ohm's law. V over R, which is 12 amps. So I will have 12 amps, and that is in parallel with the resistance, which stays the same. That one is 5 ohms. And then the rest of my circuit, I'm just going to keep that as is for now. So there was a current source going up the page, rated at 36 amps, a 6 ohm resistor, and that whole bunch goes through 1.6 ohms, and then finally to the resistor that we actually are trying to analyze, which is 8 ohms at the far end. So I can look now at this circuit and I can actually simplify it a little bit. So I'm going to redraw it with all of the current sources together. Now this is a valid transformation to make because remember it's the connectivity between nodes is what really defines a circuit. So my earlier video where I redrew a circuit layout, you could follow the same kind of procedure here. Just identify the nodes and identify the elements that are connected to those nodes, and you'd be able to see that redrawing it like this is actually a valid way to express the exact same circuit. So all of the current sources and then all of the resistors. So the resistors were 20 ohms, 5 ohms, and 6 ohms. And the end of the circuit, I'm just going to keep the same as before. So that was 36 amps. So now that I have all my current sources together, you should be able to recognize that they can combine sort of additively. So this is just using, say, KCL, like currents flowing in. I can look at all the currents that are flowing in and just combine them, and then subtract off the currents flowing out. So I will have an equivalent current source, which is going to be, if positive is up the page, then I would have 36 plus 6 minus 12. So 36 plus 6 minus 12 is 30 amps. So I can redraw all 3 of these as a single current source which is just 30 amps flowing up the page. I then have a network of parallel resistors. So all of that, which by the way I can calculate. Let's just move this down, have some space. So I will calculate here a equivalent resistance for that, which is going to be 1 over 20 plus 1 over 5 plus 1 over 6, all of that to the power of minus 1. So we calculate 1 divide 20 plus 1 divide 5 plus 1 divide 6. All of that is to power of minus 1, which is 2.4 ohms. So I can just write here 2.4 ohms, and then I have just the end of my circuit, which again I'm not touching, so that's just this portion, which is 1.6 ohms and 8 ohm resistor there. Okay, so this is looking nice, right? We've simplified this a fair bit, but I can actually go one step further, which is that I can now turn this back into a voltage source, and then I'll end up with a voltage divider circuit, which will enable me to get to the voltage that I wanted. Remember, my voltage that I'm seeking is this one here, across the 8 ohm resistor. So to turn that back into a voltage source, I draw a voltage source, I put my resistor 2.4 ohms, that goes through my rest of my circuit, that was 1.6 ohms, through my 8 ohm resistor, and the value on my voltage source here, Vs, is just going to be the Ohm's law combination of these two values, so that was 2.4 times 30, which is 72 volts. So I have 72 volts source there. I can combine these two resistors because they are in series. So continuing to draw this, I will have 72 volts. The series combination of these, so that is 2.4 plus 1.6, which is just 4. 2.4 plus 1.6 is 4. So that was the combination of those, and then 8 ohms, like that, and remembering our output voltage is there. Now we just have a simple voltage divider circuit. So our output voltage is our input voltage, which is 72, times the voltage across which the output appears, divided by the sum of the voltages. So that's 8 plus 4. So I'll now just type this expression into my calculator, and the answer that I get is 48 volts. So in this way, I keep making my circuit simpler and simpler and simpler until I get to something where the answer is pretty much obvious. Or you can solve for it directly using a voltage divider or a current divider or just plain old Ohm's law to get the answer that you're seeking.